Yeah, this talk is titled DuckDB Spatial, Supercharged, Geospatial SQL. Quick info about me. Yeah, my name is Gabrielsson. I have a bachelor's in computer science from Uppsala University. I like to say that I'm a fan turned software engineer at DuckDB Labs, where I mostly work on DuckDB's execution layer and its Geospatial extension. Now, DuckDB Labs is a company founded by the DuckDB creators. We're based in Amsterdam. We're a small company, currently around 18 people, and we provide development and support for DuckDB. All right, so what is DuckDB? DuckDB is an analytical embedded SQL database. It originally started out as a research project at the CWI National Research Institute in Amsterdam. It is free and open source, MIT licensed. There's no dual license, no open core. You get, all the code. DuckDB is also very portable. It has no external dependencies. It runs almost everywhere. And it's currently in pre-release version v0 10.3. Despite that, it has very extensive Python and client integrations to other data science languages. And I think the coolest part about DuckDB is that it really makes the most out of your laptop. Now, usually when I talk about DuckDB, in particular to people that come from more of a data science background, there is a bit of hesitation or confusion. Why would I want to run like a clunky database engine locally where I have to write my queries in this pseudo English language from the 70s? I have my notebooks, my data frames. It's so much more nicer, it's so much faster for me to iterate. So let me try to explain why I think DuckDB will not only make efficient use of your computing resources, but also your time and your patience. So I'm going to try to do that by talking about what I think are the three main focuses of DuckDB, so to speak. Those are execution, storage, and user experience. So let's just jump right into execution. Basically, any sort of query processing engine, whether or not it's a database or some cloud warehouse or a data frame, works in one of three ways. So the first way is what's called a row at a time execution model. Basically, if you imagine you want to process a big data set of tabular data, you iterate over all the rows one at a time. You chunk like one row through the pipeline at a time. And this is the classic database approach. This is how SQLite, Postgres, SQL Server, almost all classic SQL databases work. And it's great because it has a very low memory footprint. A lot of these tools are very old. They come from a time where RAM memory was very scarce and you could almost never fit your whole working set in memory at the same time. The downside of this is that it has a very high CPU overhead. You spend a lot of CPU cycles not actually like operating on your data, but just shuffling rows around and synchronizing between different parts of your pipeline. So the alternative is the column at a time model. And this is like how almost all data frame libraries work. You basically keep your entire column in memory at the same time, and it's very efficient to just iterate through that. It's already there for you. You can also, if you really want to optimize, use these modern SIMD instructions that are present in most CPUs to make it go, or to implement a lot of operations even faster. The downside of this, of course, is that you have a very large memory footprint. You need to keep your whole column in memory, and any intermediate results also have to be materialized for the whole column. So, third way to do it, that's becoming very trendy nowadays, I guess, is the vector at a time model that DuckDB, among many, use. And it's kind of like a best of both worlds. Instead of operating on a row at a time or at the whole column, you operate on a vector of rows, which is, like a chunk of rows. And the trick here is to kind of optimize this vector size so that all of your current working rows fit into your CPU cache. So you don't even have to go out to memory to access it. Additionally, DuckDB is multi-threaded. Now, this isn't actually tied to the processing model. You can write multi-threaded row at a time and column at a time query engines as well. But it synergizes very well with vectorized processing because it's very natural to parallelize over vectors. Any sort of like lock or synchronization overhead you have in a multi-threaded program, you can kind of amortize that over your vector instead. Now, the reason I bring this up is that parallelism is becoming increasingly important in 2024. Even consumer-grade laptops like the M3 chip that was announced last year, I think they even came out with a new one just a couple of weeks ago, have like 16 cores in them, which is a ton of performance you're just leaving on the table if you can't make use of that. Additionally, a kind of cool thing about DuckDB's execution model is that it's optionally order preserving, which is a behavior that is like explicitly not supported in most database engines. But this kind of gives you the same, like data frame semantics where you can kind of slice and dice rows or tables on the vertical axis and know that your input and output rows are going to be correlated. Now, this is kind of where a lot of the excitement for DuckDB tends to die down. People learn about the vectorized execution model. It's really fast. It goes really well in a lot of benchmarks. They use it to query their CSVs or Parquet files or whatever. But I think a critically underrated feature of DuckDB as well, especially for people in a more data science background, is that DuckDB as a database engine also provides you with storage. So, okay, why is this important? Here's a picture of every analytics or GIS project ever, right? You start out thinking, okay, I'm going to keep it clean. I have my data subdirectory. You get some exported CSV file somewhere. Of course, it's dirty. You have to manually clean it yourself. You got your shape files. There's some auxiliary file missing always. You have some GeoJSON, but you have to manually split it up into multiple parts because GeoJSON is a terrible format. You start out with your main py, then you realize it's too annoying, so you switch to a notebook instead. At some point, your coworker asks you to send over some data, so you just zip everything and drop it into Google Drive. You have your worker script to run some annoying batch job in the background. And at some point, finally, you realize you get some useful result. You produce your Parquet file because you want to leave the world in a better place than you found it. But of course, Parquet doesn't do updates, so obviously something was wrong, and you end up with the dreaded final v2. The thing is, if you recognize this picture, then you need a database. This is the exact problem that like a database is trying to solve, managing your data. And by not using a database, you have offloaded all this work onto you, basically. So this is another reason why I think DuckDB is pretty compelling. DuckDB provides a storage backend. It's a common misconception that DuckDB is an in-memory database. That's not true. DuckDB has a database file format where, similar to SQLite, one database is represented as one file. So it's very easy to share and back up. And also, because this is a proper database, it supports updates. You have these ACID properties that most databases usually provide. Also, you have transactions, which, again, criminally underrated feature. Even if you are the only one operating on your data in your database, having access to transactions is great because you can set up this big transformation pipeline in a transaction. You can create tables, delete tables, update tables, whatever, and you know that either all of this is going to succeed or nothing is going to succeed, and the database is going to revert back to its previous state. Of course, you can store multiple tables in one database, but internally, DuckDB will also store the columns individually on disk. This is pretty great because DuckDB also stores fast, or like per column statistics, basically, so it's very fast to search on disk for specific values in specific columns. Also, because columns are stored separately, we can apply specialized lightweight compression algorithms on these. Data that's like in the same column usually compresses much better than if you do it row-wise. They have the same data type and they usually share the same sort of distribution, right? So there's no less entropy, I guess. And in practice, this can save you almost 3 to 5 times on storage use. And paradoxically, this also improves query speed. Even though you're doing more work to compress and decompress, when you're reading data from disk, the bottleneck is not actually your CPU, it's your disk. So it's much faster to store data compressed and decompress it in memory than it is to store data uncompressed and try to read it back. So this is a short of how DuckDB's compression has improved throughout the years. This is actually a pretty old figure. This is like, the last one is 0.6, we're on 0.10 now. We actually have this new compression algorithm out of CWI that is like super state of the art for floating point compression. I don't have any numbers on it, but it replaces both the FSSD and chimp. So I expect this number to be even better today than it was in 2022. All right, lastly, I want to talk about UX. So DuckDB has this in-process deployment model, meaning there's no separate server. So there's no config, there's no environment, God forbid, there's no Docker. And a great thing about this is that you also have very minimal transfer delay / overhead to get data in and out of DuckDB. If you have, I don't know, compute some big result in Postgres and you want to pull this into your notebook, Postgres first has to serialize this result into some binary encoding, ship that over the wire, and then deserialize it back in your client library, and then eventually it ends up in Python or whatever. But because DuckDB runs in process, you can skip almost all of that. This also means it's very easy to run DuckDB as part of a larger system, not just as an end user tool, but also as a component in a bigger, I don't know, data warehousing solution, right? So you can run DuckDB, of course, in the backend, just slap together a fast API server and import DuckDB. You can run it in the client if you have some sort of client application. It even runs in the browser using WASM, which of course isn't as fast, but it's much faster than JavaScript. And it also even runs on your phone, and I think my watch, but I haven't tried. Now, because DuckDB runs in process and shares the resources with your program, it tries to be a good guest, so to speak, by doing what we call graceful degradation. Now, this doesn't really sound like something a good guest would be up to. Like you don't really want to invite somebody over to be gracefully degraded, but graceful degradation is basically the answer to the question, what do you do when you run out of RAM? And in DuckDB's case, this means that almost all operators, the different parts of the database engine that executes different parts of a query, will spill to disk, meaning they will offload their intermediate result into a temporary file on your hard drive and then keep processing, and then in the end try to reassemble the final result. So the idea is that DuckDB should never crash, always make progress in some way. But this isn't just about not crashing. This is a figure from a paper very recently published by my dear colleagues Lawrence and Hannes, together with Peter Bones, comparing DuckDB with some other database engines, running this big kind of group by query, where on the x-axis it's kind of the size of the data set, and the y-axis is execution time. And all of these databases run with a memory limit of 32 gigabytes. So you can see how once you reach that 32 gigabyte dataset size, some of these engines tend to either abort or time out, or they get this really sharp performance spike where they need all of a sudden to read stuff from disk. While DuckDB tries at least to have more of a smooth transition, to not just immediately hit this wall once you run out of memory. Okay, so these are all things that run kind of under the hood to make DuckDB, or using DuckDB, a more pleasant experience. But we also try to make using DuckDB for the end user nicer. One of these things is what we call friendly SQL. So DuckDB SQL dialect is this superset of the Postgres dialect. We actually use their like parser implementation, or used to use anyway. So we have a lot of funky syntax extensions, like from first syntax. You can swap the from and the select. You can do group by all, dynamic column selections, which are really nice if you have tables with a ton of columns, nested types, lambda functions. Also a lot of like Python-inspired stuff, like list comprehensions and this kind of unified function call syntax where you can pretend functions are methods. Speaking of Python, DuckDB has a very special relationship with Python. It is by far, I think, our most well-developed like client integration. We actually have 3 different Python APIs. So there is the standard like Python DB API. If you used any other database through Python, this will look familiar with connections and cursors and whatnot. We also have this kind of crazy new thing where we try to implement a PySpark compatible API. So the idea is that you can just drop in, replace your PySpark code with DuckDB instead. But I think by far the best way to access DuckDB is through this relational API. And this is pretty cool because basically how it works is that you kind of chain together these operators through Python. But this is a completely lazy API, meaning nothing actually gets executed until you have like one of these terminating statements like show or toTable or fetch. And the cool thing about this is that you can kind of focus on just composing your query kind of imperatively, like it was a data frame, right? But DuckDB still has access to the entire query plan at once you call show. So DuckDB can use all of the different like optimizations and query rewriting and reorder your operators to be more efficient. And you don't have to think about that. You just write it as you want to. We also have this really cool thing about with zero copy data frame interoperability. So in this case, you can create like a pandas data frame and then query it directly from DuckDB. You just say from df, and DuckDB will then look up anything in scope that looks like a data frame and read that memory immediately. You can also convert your results back into data frames if you want to continue working in data frame land. Use, kind of these methods and functions that DuckDB doesn't support, like plotting, right? And this also works with polars and NumPy and PyArrow as well. So yeah, it allows you to scan data frames and arrays in scope directly from memory. As I said, polars, NumPy, pandas, and PyArrow. And this is like a product of being an in-process database. This is only really feasible because we share the same address space as pandas or Python in this case. So the idea is that you can use the best tool for the job. All right, so far, what's missing? Spatial support, of course. So DuckDB has this thing called DuckDB Extensions. These are basically compiled code modules, I guess, or plugins maybe. They are downloadable or loadable at runtime directly from within DuckDB, and they can provide types, functions, operators, optimizer rules, scans, all kinds of crazy stuff. You can write your own if you're proficient in C++, but at DuckDB Labs, our philosophy is basically that anything that isn't essential to DuckDB should be an extension. So we basically support and provide all of the available extensions that you would use in practice, like extensions adding JSON support, integrations with Postgres, MySQL, SQLite, AWS, Azure, and of course, Spatial. So DuckDB Spatial is the extension that I've been working on during my time at DuckDB Labs. It is a official extension, supported extension by us that adds geospatial capabilities. It does this through this simple features vector geometry type. So you can store points and polygons and line strings, all that good stuff. And this is kind of modeled after what PostGIS supports. DuckDB itself is kind of inspired by Postgres, so it makes sense that we try to follow what PostGIS does for the geospatial extension. It's also kind of where my background in GIS, where I have most experience. So we're not like fully compatible yet, but we provide, if you count overloads, 100 plus of these ST functions already. So most things are there. Now, crucially, like DuckDB, this extension doesn't have any runtime dependencies. We actually statically bundle geos and proi into the binary, so we will never conflict with whatever you have installed locally. We also embed like the whole default proi prediction database, so DuckDB Spatial will recognize like over 3,000 like of the most common CRS definitions out of the box. And of course, we ship this as pre-built binaries for over 10 platforms. So it's supported in Windows, Linux, Mac OS, even WebAssembly. All right, so quick demo of using the Spatial extension together with some Python. First off, we just import DuckDB. We're gonna install and load a Spatial extension. It looks like this. You just write a SQL, install Spatial, load Spatial. That's it. No other setup required. I have this extract of the New York City taxi dataset with 1 million rides in Parquet format. We're gonna create this relation that basically scans this Parquet file. Now we can also execute, we're gonna drop down into SQL for a bit and execute this summarize clause. It's not exposed into the Python API yet, but basically summarize will compute a bunch of statistics for any query, but we really just care about the column name and column type to figure out what this Parquet file really contains, right? So that's gonna look like this. Now, yeah, the only thing we really care about here is the pickup longitude and latitude, and I think the trip distance as well. So we are going to convert these latitude and longitudes into geometries using this stPoint function. If you're familiar with Postgres or PostGIS, this should all not come as any surprise to you. So yeah, we execute the selection and then call toTable to actually create a table in our database from this relation. Now, this longitude or latitude and longitude is in VGS84. This taxi dataset, of course, is localized to New York City. So let's also transform it into a CRS that is more suited for this region using the transform function where you pass a source and a target SRID. Now, okay, if you look at this and think, wait a minute, I thought the whole thing with the Python API was that I didn't have to write SQL. This looks like an awful lot of SQL. Don't worry, I got you. So normally when we pass kind of expressions through this relation API, you can pass it as a SQL string, and DuckDB will then figure out and parse this, realizing that, okay, this point is stPoint is a function, pickup latitude and pickup longitude are both columns that are in scope. But you can also create this expression manually through Python using this function expression class, where you pass the function name and then any parameters. Now, okay, we have kind of hard-coded column names here, so let's create a function instead that returns this expression. So it's going to look like this instead. So we now create this makePoint function that is converted into, or returns a DuckDB expression to create a point. We're going to do this with transform as well, in which case it looks like this. Now, in transform, the parameters are strings, right? The SRIDs. So we're going to use this constant expression instead of just passing a normal string to really tell DuckDB that this is a string. Don't try to think about this as a column. And we're going to be a little bit cheeky. We're going to attach this to the expression class itself. I know this is like not really, this is kind of frowned upon in Python, but we're going to do it anyway. So now that we have these helper functions that produce expressions, instead of having this big SQL string, we can use them instead, and it's going to look like this. Much nicer. Right, so we have our data now as, or we have this expression or relation to create geometries. It would be nice if we could also use our spatial knowledge to do some data cleaning. If you worked with this taxi dataset before, you know it's a very noisy and messy and kind of dirty dataset. So I'm going to convert our relation back to a relation and also add this distance expression to calculate the distance between the pickup point and the drop-off point. This ESRI 102.718 projection is in feet, so I'm going to divide it by 5,280 to turn it into kilometers again, which is the same unit used by the trip distance in the original dataset. So now we can filter out and say, okay, how many of our taxi rides have a trip distance that is smaller than the aerial distance, right? That doesn't really make sense. So if we count that, it's going to tell us 65,000, right? So for 1 million rides, this is a, yeah, pretty dirty data set, I'd say. Now, instead of computing this count, I'm actually going to turn this back into a table producing relation, but injecting the filter instead. So we now have created this kind of cleaned, or a little bit cleaned at least, rides data set. Let's also look at creating some taxi zones. So I mentioned the DuckDB Spatial integrates with GDAL out of the box, so you can check or list all of the GDAL drivers available to you by invoking this stDrivers table function, and it's going to look like this. Now, the thing that I'm really interested in here is, of course, shapefile support. So it's good to see that that's supported. I happen to have the shapefiles locally, so I'm going to invoke this stRead function provided by DuckDB Spatial that basically calls into GDAL to read any sort of spatial data sets. Now I'm going to join this with my cleaned rides and use the st within spatial predicates to get all of the, to join, yeah, all the rides with the zones that they are, dropped somebody off in. Now I'm also going to aggregate this to kind of count how many trips was in each zone. I'm going to sort them by descending. And if I then call show and finally execute this expression or relation, I'm going to get this result. Cool. But wouldn't it be great if we could also visualize this result some way? Of course, even though DuckDB can't do it, I know somebody who can. So I'm going to change this aggregation to also return the geometry of the zone, but I'm going to convert it into WKT. Now I'm going to turn this relation then into a pandas data frame, which I'm going to turn into a GeoPandas data frame, which I then can plot. And then it looks like this. All right, so this was kind of like a baby example of how to use Spatial together with Python. Actually, I think if you were to do this in GeoPandas like straight up, it would probably be faster because this data set is not really big enough, or the queries aren't really complex enough for DuckDB to really shine. I mean, everything fits handily in memory. But hopefully, it was illustrative at least on how to do some basic spatial operations. Now, I really quickly want to end on some notes about limitations and kind of future work for Spatial. So far, I've been really focused on the kind of internal infrastructure of Spatial, like having an efficient representation of geometry internally, also pushing a lot of stuff into DuckDB core, like exposing a lot of APIs, internal APIs, so we can make use of them in Spatial. But the plan now, like I managed to land a lot of really big things that I'm very excited about. So the plan now is to kind of build on top of this foundation that we have and provide some of these kind of long-awaited features like spatial indexes, better projection handling. As you saw, you had to kind of juggle the projection information around yourself. That's going to change hopefully soon. Also more functions, of course. Also, the documentation is a little bit lacking. But we have like a new kind of documentation system underway at DuckDB Labs. And of course, I want to spend more time to work on better integrations with like GeoParquet, GeoArrow, maybe GeoPandas as well. In the example I showed you, I had to create this geometry into WKT and then feed it into GeoPandas. I think in the future, maybe if like when both GeoPandas and DuckDB Spatial has better support for GeoArrow, you can kind of do that natively and treat GeoPandas data frames just as DuckDB can treat normal data frames. Now, also, of course, add better support for Spatial in client libraries. It was nice because I could kind of show you now how to create these expressions, but it would be also great if DuckDB Spatial could provide a lot of these Geospatial expressions out of the box as part of the Python API, so you don't have to create them yourself. Now, despite this, there are some people that have been kind of building things on top of DuckDB Spatial that I just really quickly like to shout out. So there's this project called QuackOSM by Kamil Rakciki at Wrocław University. It's a tool to work with OpenStreetMap data. It provides a lot of like convenient user features, automatic download and like selection given at certain bounds. You can export things as GeoParquet. It exists both as a CLI and a Python module. It's really fast. And yeah, next time you want to extract some OpenStreetMap data, I'd highly recommend to give it a shot. Also, if you've heard of IBIS, it's actually a project out of Voltron Labs. It's kind of this universal interface to databases and data frames. It has great support for DuckDB in general, but Nati Clementi has also been adding support for DuckDB Spatial's kind of Geospatial expression here. So if you weren't too impressed with the Python relational API and you want something more data framey, then give IBIS a shot. Yeah, and they also expose DuckDB Spatial's like GDOL integration, which is pretty nice. Also, lastly, I want to give a shout out to Dr. Qisheng Wu's spatial data management course. So Qisheng is a professor at the University of Tennessee. He runs this course, Geog 414, about geospatial data management, but he's published all the course material available online. So there's like a web book and YouTube videos. I think there's even like lab exercises. I know you guys are already deep into the geospatial sauce, but if you want to learn more about Python and GMap and DuckDB and PostGIS, this is a really good resource. Now, of course, there are many more things as well I'd like to talk about. I know if you saw Kyle Barron's talk yesterday, there's like DuckDB support for Longboard. I think there's a dbeaver plugin, a QGIS plugin. I haven't used them myself, but there's definitely things happening in this space. So quickly to conclude, DuckDB is a portable analytics embedded database. It gives you kind of the best of databases and data frames. Next time you have trouble installing GDAL, give the DuckDB Spatial extension a try. And yeah, keep an eye out because there's lots of cool stuff on the way. Thank you.
Thank you very much, Max Gabrielsson. Any questions?
Thank you for the exciting talk. I have one question. Can you use ND arrays with DuckDB? And if yes, should you at all?
Sorry?
N-dimensional arrays, like multi-dimensional arrays.
Yeah. So I think, or
Mike,
I guess
please.
I want to stand here. Yeah. I guess you're asking about raster support, right? I guess you're asking about support for raster data, maybe. Yeah. So, okay. We actually got a really impressive contribution from a third party that added support for managing rasters, or at least work in progress support for managing rasters through GDAL in DuckDB Spatial. I think I will eventually have a look at merging that. I don't necessarily think that rasters are a good fit for DuckDB's execution model, right? A big problem that I've had to deal with, a big challenge with even just vector geometries, is that geometries tend to be pretty big, and DuckDB as a vectorized engine needs to keep a lot of things in memory at the same time. Yeah, rasters are a lot bigger than vectors. Like if you were to load, I think the standard vector size in DuckDB is like 2048 elements. So if you were to load like 2048 rasters that are like 512 times 512, 4 bands, you're looking at like 2 gigabytes for just a single vector. And DuckDB creates a lot of these. So I don't know. I think we might maybe have something in that. I think we might support it soon, but it's going to be like use at your own risk kind of thing. Yeah.
Yeah, I have a question. Do you support three-dimensional
Yes.
shapes?
This was one of the big things that I've been working on this spring. Yeah, like PostgreSQL, we support Z, M, and ZM.
Also intersections and all these functions?
If Geos does it, then we do it too. I don't know. I think intersections are probably 2D as far as I can tell in Geos so far. Yeah.
Any more questions? Okay, that's it. Thank you very much, Max, again.
Thank you.